We have now been introduced to all the actors: protons, neutrons, electrons, photons, intermediate vector bosons, and the whole cast of characters. Now what we need to do is hear the dialogue. How do these particles talk to each other? Which converse with which? What are the hierarchies and who speaks the loudest? All of this we now understand with high precision through the standard model of particle physics. The key ingredient in particle intercourse is, of course, energy. To animate the static picture of atoms and their constituents that I described in Lecture 2, we need to introduce the concept of energy. Energy is defined as the ability to do work. It is a manifestation of the four fundamental forces of nature, the pushes and pulls that make particles move. Gravity is the force that arises between two objects that have mass. Gravity is always an attractive force, and the strength of the force is proportional to the mass of the two objects and inversely proportional to the square of the distance between them. That is, if I have two objects and I double the mass of one of them, the force between them will be twice as great. If I double the distance between them, the force will be 1/4 as great. Although we experience gravity as the dominant force in our lives because we live on the surface of this very massive body, the Earth, gravity is in fact by far the weakest of the fundamental forces, more than 1 trillion times weaker than the next strongest force. As a consequence, gravity plays essentially no part in the structure and behavior of atoms. Indeed, students sometimes make this mistake and think, because of the planetary model of the atom, that the nucleus, this massive object, is holding the electron in its orbit by gravity. Nothing could be further from the truth. If gravity were the force involved, then the size of a hydrogen atom would be greater than the size of the universe. The force between the electron and the nucleus due to gravity is incredibly weak and completely ignorable in all of our future discussions. We will see, however, that gravity is crucial in the manufacturing of the atoms themselves and of their nuclei inside stars. The particle that communicates gravity from one place to another, the reason the Earth knows the sun is there and so can continue going around, is called the graviton. It has no mass, and it travels at the speed of light. It has rather peculiar wave-like properties. Indeed, a gravity wave passing through this room would make the space in this direction compressed while the space in this direction expanded, and half a cycle later, vice versa. So a gravity wave looks something like this. Electromagnetism is the force that rises between two objects that have charge. Unlike mass, there are two signs of charge, positive and negative. So electromagnetic forces can be either attractive, if the two signs are opposite, or repulsive, if the two signs are alike. For example, with these magnets, it can be repulsive or attractive. The strength of this force is proportional, analogous to gravity, to the size of the charges of the two objects. Double the charge, you get double the force, and again, inversely proportional to the square of the distance between them. Double the distance, 1/4 the force. Electromagnetic forces are the ones that dominate on human scales. From atoms to mountains, and everything in between is held together by electromagnetic forces. To illustrate the enormous difference between the strength of the electromagnetic force and the gravitational force, consider this experiment. If someone were standing next to me over here, and they had just a 1% excess of positive charges, and I had a 1% excess of negative charges, we would come together with such a force that we would knock the Earth out of its orbit around the sun. Electromagnetic forces are enormously strong compared to gravity, but we don't experience them on an everyday basis because of the exact neutrality of matter, the perfect balance between positive and negative charges. As a consequence of the pattern of electron orbits, and all of chemistry is a result of electromagnetic interactions. A slight excess of positive or negative charges around an atom lead to bonds between atoms, but these excesses are very tiny. The particle that communicates electromagnetic force, the way the electron knows to keep going around the nucleus of the atom with their opposite charges, is the photon, also known as light, which is fundamentally an electromagnetic phenomenon. Like a graviton, a photon is wave-like, although the wave is more like a water wave, more what you're familiar with, and a photon also has no mass and, of course, by definition, travels at the speed of light. Unlike electromagnetism and gravity, the other two forces of nature, the nuclear forces, only operate on tiny length scales, the length scales relevant to the atomic nucleus, about 10 to the minus 14, 1/100th of a trillionth of a meter. There are two nuclear forces operating in this domain: the weak nuclear force, which can change the flavor of a quark inside a proton or a neutron, from an up to a down or a down to an up, and, as a consequence, we shall see, is responsible for the radioactive decay of atomic nuclei. The weak nuclear force often involves neutrinos, these ghostly subatomic particles that can pass right through matter. And it is the only force these particles can feel. The weak nuclear force is carried around by three different little communicators, the intermediate vector bosons. The strong nuclear force acts on the property of quarks that we call color charge, which really has nothing to do either with colors of light or with electrical charge. It's just when we start operating on this world that's so remote from our direct interaction that we sort of run out of terms and we start making up things. So each quark is endowed with a property called color charge, and the color charges are attractive to each other. That attraction is manifestation of the strong nuclear force. The strong force is always attractive, and it holds the quarks together inside the protons and neutrons. Again, in the conditions of the universe today, the quarks never are allowed free. This force is 100,000 trillion times the strength of gravity. It's carried around in its tiny little domain of the nucleus by a particle called the gluon. The residual attraction of these quarks for each other, the exchange of gluons constantly inside the proton or neutron, a little bit of that leaks out, and that helps attract the protons and neutrons to each other, holding the nucleus of the atom together against the electromagnetic repulsion that all those positive particles packed into a small space actually feel. Just like molecular bonds, where the asymmetric distribution of positive and negative electric charges holds atoms together, inside the nucleus, the asymmetric distribution of the strong force inside the proton and neutron holds the protons and neutrons together to make the atomic nucleus. These forces that I've just described, gravity, electromagnetism, the weak force, and the strong force, result in pushes or pulls that make particles move, manifesting energy. Again, energy is the capacity to do work. Unrealized energy is called potential energy. It's a stored form of the ability to do work. Gravitational potential energy, for example, is represented by the water at the top of a waterfall. Once it plunges over the edge, it can do work, turn a water wheel or a turbine and make electricity. But when it's sitting on top, it's just the potential it has to do work. Electromagnetic potential energy is represented by a battery, where the positive and negative charges are separated from each other. They want, of course, to come together. They're waiting to come together, but you hold them apart with the potential to do work. When you flip the switch, they flow and they can do work. Electromagnetic potential energy is also manifest in the electrons in their orbits around the atoms. We can move them around, rearrange them, and produce light or release chemical energy, as in an explosion. But their locations represent potential energy until the emission of light or the rearrangement in a chemical reaction. Likewise, nuclear potential energy is stored in the arrangement of the nuclear particles inside the nucleus, which can come together through the process called fusion, split apart by the process called fission, or in other ways transform the quarks inside the protons and neutrons in a radioactive decay, all of which releases energy. Energy in action is actually doing work, and it comes in many forms. Gravitational energy is released when a meteor strikes the Earth, or that water comes over the waterfall and turns a turbine. Electromagnetic energy travels along in the form of light. Nuclear energy is released in radioactive decay or in fusion, the process by which the stars make the elements. The energy of a moving body is called kinetic energy. Heat is also a form of energy, which is actually represented by motion of atoms and molecules on the atomic scale. Our model for heat provides a vivid picture of the behavior of atoms and molecules and how energy governs all. Heat, you see, is just the motion of individual particles, and temperature is the number we use to measure the average kinetic energy of those particles. The temperature of this room is set by the rate at which the atoms in the air in the room are running around and colliding with each other. Their speed determines the temperature. If I turn up the thermostat and heat up the room, what that means is I've speeded up the motion of the molecules in the room. If I turn on the air conditioner and cool down the room, it means I've just slowed down the motion of the molecules in the room. Temperature is just a measure of the average kinetic energy of the molecules. This simple model for heat explains a number of everyday phenomena, which it's useful to picture to understand that heat really is the energy of individual atoms. Why, for example, do you burn your skin if you touch the wall of a hot oven? And why don't you burn your skin if you just reach into the oven and pull out the tray of chocolate chip cookies to see if they're done? Why does the atmosphere not fall down? Atoms are made of molecules. Molecules have mass. The Earth has mass. Masses attract each other. Why doesn't the air fall down? Why don't we have to crawl around on our hands and knees to breathe up air atoms? And why the little droplets of water on the plates that you wash and leave on the counter to dry disappear overnight, despite the fact the temperature in the room never gets anywhere close to the boiling point of water, the point at which water goes from a liquid to a gaseous phase? All of these simple everyday phenomena are easily explained by our model for heat. You get burned when you touch the wall of a hot oven because hot, in the case of the wall of the oven, means those molecules are jiggling really, really rapidly next to each other. And when your skin, whose molecules are moving much more slowly, touches it, the rapid motion breaks the bonds that make up the molecules of your skin, changing skin into something that looks more like charred flesh. Now, the wall of the oven might be 400 degrees, and that 400 degree number characterizes the rate of the jiggling. The air in the oven is also 400 degrees. How come you can stick your hand in there without it turning out looking like charred flesh? Well, the difference simply is the difference between a solid and a gas. Recall that in a solid, the atoms are touching each other. And so there's lots of atoms that get to interact with the molecules of your skin and pound them apart. In the air, the molecules are this far apart from each other, 10 times their radii. So there's only 10 by 10 by 10, 1/1000th as many molecules. If you leave your hand in the oven with the chocolate chip cookies for 20 minutes, it'll come out looking like a chocolate chip cookie. But if you leave it in there just for a few seconds, only 1/1000th as many molecules will collide with your skin, and the damage will be ignorable. Why doesn't the atmosphere fall down? Well, the answer is, to first order, it does. It does fall down because the particles in the air do have mass, and the Earth has mass, and it attracts them. But the temperature of the air determines the speed of the molecules, and that speed is really quite extraordinary. At room temperature, the molecules are on average, moving about 450 meters per second, half a kilometer per second. A molecule moving that fast and traveling straight up will go up 10,000 meters before it turns down and falls down again. That's as high as Mount Everest. So, the air does fall down, but because of this rapid motion of all the particles that make it up, it often gets to high altitudes before it turns around and falls down. Just as when I toss this orange in the air, it goes up before it falls down. The average speed is 450 meters per second, but all the atoms are not moving at the same speed. There's a distribution of speeds, because some particle sitting here may get bombarded by 3 particles simultaneously from this side and take off in a rapid speed over there, where these other ones would have slowed down. So there's slowly moving molecules and rapidly moving molecules. And the faster ones are moving 5 or 10 times the average speed. The little water droplets on the plates that you leave on your drying board overnight are jiggling around and have an energy distribution that's represented by this curve where some molecules are moving faster and some are moving slower than the average. As a consequence, the most rapidly moving ones are in fact moving fast enough to escape their bonds that hold them in the liquid phase and move off into the air. So the most rapidly moving molecules can escape without the average molecule being moving anywhere near the speed that boiling water would move. Well, when the rapid ones escape, clearly the average velocity shifts down a little bit, and so you think, okay, so fine, then the drop will get smaller, but it'll still be there in the morning. However, that molecule is, that drop of water rather, is in equilibrium with all the other molecules in the air moving around in the room, which are constantly colliding with it, and speed up the molecules again after they've slowed down, and repopulate the end of that distribution with the very highest speed molecules, which in turn can escape. So as this process repeats over and over while you're sleeping, all the molecules of water go from the liquid state to the gaseous state, despite the fact the temperature has never risen anywhere close to the boiling point. The other thing to note about this distribution of particle speeds is that the heavy ones move slower than the light ones. Imagine a billiards table, and you put a bowling ball in the middle, plus a bunch of pool balls, plus a bunch of ping pong balls. Well, if you broke in that circumstance, the ping pong balls would go flying off the table, the bowling ball would barely move, and the billiard balls would bounce off the rails as they normally do. The distribution of energy is equal, but when the distribution of energy is equal, the heavy ones move slowly and the light ones move fast. This will turn out to be crucial in several of our examinations of history through the eyes of an atom. Some units of energy are familiar, while others need to be defined for our atomic scale, which is far from the human scale. The basic metric unit of energy is the joule, a word you may not be familiar with, but 1 joule expended in 1 second represents a unit you are familiar with, the watt. A joule per second is 1 watt of power. A light bulb produces 100 watts, or expends in energy 100 joules per second. The other unit that might be familiar is the calorie. Calorie with a capital C, or for the chemists amongst you, a kilocalorie, 1,000 calories with a small c, is also a metric unit. It's the amount of energy it takes to raise 1 kilogram of water by 1 degree centigrade. To raise my body temperature from room temperature, which it would otherwise be, 20 degrees centigrade, up to its normal operating point, 37 degrees centigrade, or 98.6 degrees Fahrenheit, means I need 17 degrees centigrade of temperature rise times about 50 kilograms of water. I'm mostly water, and I'm about 50 kilograms, or 850 calories. A big ice cream sundae. Now, if I only had to raise that once, then I'd only have to eat 1 ice cream sundae, and that would be it for eating for the rest of my life. But of course, while I'm standing here talking to you, I'm expending energy. And in particular, by simply standing still, I'm radiating away 100 joules per second, or 100 watts of energy, exactly the same amount as a light bulb. That energy is leaving my body, the jiggling atoms are slowing down, giving off energy in the form of infrared light out into the air in the room. And so I have to constantly replenish that energy with the stored chemical potential energy I find in food. How much then do I have to eat? Well, 100 joules per second times the number of seconds in a day, which is 86,400, times the conversion of calories to joules, which is 4,186 joules per calorie, means I have to eat around 2,050 calories a day. Around 2,000 calories a day just to keep my body temperature above room temperature where my body comfortably operates. If I do anything else, go out and run a marathon, for example, or even stand here vigorously talking to you for half an hour, I have to eat more calories than that. All the better for me, because I love to eat. Now, on the tiny atomic scale, we have a different set of energy units because the macroscopic units useful on our scale are inappropriate. We define the electron volt as the unit of energy. And you can think of this as you put a single electron on one pole of your car battery and let it run across to the positive pole of the battery, it would gain 12 electron volts. It's the amount of energy that a single electron would gain moving through a potential of 12 volts. Typical chemical reactions, the rearrangement of the electron shells of atoms with other atoms, release at most a few electron volts per molecule. The electrons are bound to the nuclei of atoms, the tightness with which they're held together, the amount of energy I have to add to remove one, by a few tens of electron volts up to many thousands of electron volts. And typical nuclear reactions, the release of energy when nuclear particles rearrange, are in the millions of electron volts. Now, what about the detailed architecture of the atom? How do these forces all conspire to produce it? It's going to be important to understand these details if we're going to use them as our historians. Niels Bohr developed a model for the atom in the early part of the 20th century, which has enormous explanatory power. Remember, however, it's a model. It should not be taken literally. Indeed, it's not even clear what we mean by what the subatomic world looks like literally. It's so far removed from our experience, we can't possibly have a visceral feeling for it. But we can build models of it that predict its behavior, and that's the principal role of science. Every type of atom in the Bohr model has a unique set of levels in which electrons can reside, a unique set of orbits spaced at different distances from the nucleus. Each of these is labeled by how tightly the electrons are bound, or, to put it in the opposite sense, how much energy I'd have to go in with a set of tweezers to pull the electron out. The amount of energy needed to remove them is called the binding energy. Now, each energy level, each different orbit at a different distance, has a set of sublevels that are at slightly different energies themselves. Level 1 has one sublevel, level 2 has two sublevels, level 3 has three sublevels, and so forth. Each sublevel has a maximum number of electrons that it can comfortably hold. Sublevels 1, no matter which energy level it's in, can always only hold 2 electrons. Sublevel 2 can hold 6, sublevel 3 can hold 10, sublevel 4 can hold 14, all in increasingly complicated dances as the electrons orbit the nucleus. Now, the periodic table, first developed by Mendeleev in 1869, is arranged to reflect how the sublevels are filled up. Because the important thing in the way atoms interact with each other is the way the outermost electrons are arranged. The outermost electrons are the ambassadors to the outside world for the atom, and they determine how it joins up with other atoms, or in some cases, doesn't join with other atoms. So the periodic table is arranged such that atoms in the same column of the table have similar arrangements in their outermost electrons, thus making their chemical behavior, their ability to combine or not with other atoms, similar. Atoms in the same row across the periodic table have the same principal outer energy level. So, looking at the periodic table, row 1 has only 2 elements: hydrogen, 1 proton, 1 electron; helium, 2 protons, 2 electrons. Sublevel 1, as I said, or level 1, only has 1 sublevel, and it can only hold 2 electrons, so end of story. Row 2 in the periodic table has 8 elements in it. Lithium, which now, with its first level full of 2 electrons, goes to level 2 and adds a 3rd electron there, so has 1 electron in its outermost shell. And beryllium, which has the 2nd electron in sublevel 1 of level 2. Then we move to sublevel 2 of level 2, and we find boron, carbon, nitrogen, oxygen, fluorine, and neon. 6 more elements because there are 6 electron spaces in the hotel at sublevel 2 in energy level 2. Row 3 goes to energy level 3, sublevel 2, the first 2 elements, then the next 6 elements, and then the table starts to get more complicated because the levels and the sublevels start overlapping. But the critical point is that the columns still represent elements that are chemically similar to each other. Hydrogen, lithium, sodium, potassium, those in the first column all have that 1 electron hanging out in the outermost shell. All the other shells are filled, and that 1 electron is sitting there. This makes these atoms quite reactive because the electron is lonely. It wants to join up with something else, or it wants to be donated to another atom, and therefore those atoms really want to join up with other atoms. Whereas on the opposite side of the periodic table, where we have helium and neon and argon and krypton and the noble gas elements, as they're called, we have atoms in which the outermost shell is completely full of electrons. It's satisfied, it's happy, it doesn't need to join with anything else, and that's why these are called the noble gases. They're noble in that they don't mix with the hoi polloi, they are atoms that never form chemical bonds. The sometimes partial sharing of electrons between atoms, or just the asymmetric distribution of their charges in the atom, is what binds atoms together to make molecules. H2O is the simplest example. You have an oxygen atom that's sitting there. It's got 2 electrons in the first shell, 2 electrons in the next shell, and 4 electrons in the next subshell, meaning it has 2 holes. 2 hydrogens happen along. They each have 1 electron in their outside shell, which is looking for companionship, and they join on. 2 hydrogens sitting like little Mickey Mouse ears on top of the big oxygen atom. the electrons tend to hang out more with oxygen, making that side of the molecule negative, and the electrons from hydrogen also hang out with the oxygen, making the opposite side of the molecule positive. This allows water to take on its unique characteristics, which, as we will see, are somewhat important in the origin of life. Because the size of the orbits of atoms is determined by the strength of the electrical attraction between the nucleus and the encircling electrons, the bigger the nucleus's charge, the smaller the first orbit is, and the more tightly the electrons in it are bound. In hydrogen, the one electron is attracted to the proton with an energy of 13.6 electron volts. That is, if I wanted to remove that electron, I'd have to add 13.6 electron volts of energy. In uranium, with 92 positive charges in the nucleus, that first electron, the one closest in, is bound with an energy of 115,000 electron volts, much more tightly bound because the electrical force is proportional to the product of the charges, meaning it's 92 times stronger. Now, since the outermost electron, the last one added to an atom, effectively sees only one unbalanced positive charges, the electrons interior to it having canceled out all the other particles, all the other charges in the nucleus, all atoms are about the same size. The size of the outermost orbit determines the size, if you will, of the atom. Hydrogen with one proton and one electron is roughly the same size as uranium with 92 protons and 92 electrons, because the outermost electron of uranium still only sees a net of one positive charge, and so has roughly the same attraction as the one electron to the one proton in hydrogen. Now, in addition to interacting with neighboring atoms, electrons can jump around inside an atom, and the jumping of electrons from one level to another causes the emission and absorption of light. An electron will jump if it gains the energy to climb from the level that it's sitting in to a higher level in the atom. It could do this in one of two ways, either by absorbing a photon, a little packet of light energy, which boosts it to just the right level, or through the collision of another atom which comes along, bounces into it, and knocks the electron up. When an electron jumps down from a level that's too high, it emits energy, usually in the form of a photon, which corresponds in energy to the difference between those two levels. Here's the example of hydrogen. The levels in hydrogen are 13.6 electron volts, 3.4, 1.5, 0.85, etc., going all the way up to the edge of the atom. If an atom comes along and collides with a hydrogen atom, or if the hydrogen atom gobbles up a photon that corresponds the difference between, say, level 1 and level 3, 12.1 electron volts, the electron will jump up there. Then, because it doesn't really belong there, spontaneously, it's likely to jump down. It could either jump down to level 2, in which case it give off the difference in energy in a photon, 1.9 eV, which corresponds to red light, or it could jump all the way back down to where it came from, 12.1 eV, giving off a photon in the ultraviolet part of the spectrum. The structure of the nucleus has energy levels that are analogous to those of the electrons in the atom. The quarks, confined inside the proton and neutron by the exchange of gluons, are carrying the strong nuclear force which acts on the quark's color charge. The asymmetric distribution of that color charge leaves some of the strong force leaking out to bind the protons and neutrons into the nucleus. Just as in the atom, changes of energy levels of protons and neutrons inside the nucleus can either absorb photons or give off photons, a feature of the atom which we'll take advantage of when we study some of the artifacts of history. The spontaneous rearrangement of nuclear particles leads to radioactive decay, providing a clock that runs imperturbably through all of history, as we shall see in Lecture 5. The concept of spontaneous nuclear transformation, the realization of the dream of the alchemists of turning one element into another, arrived with the dawn of the 20th century. It took most of the last century, however, for the full potential of this phenomenon to be realized. Nuclei provide a set of imperturbable clocks and a host of unalterable tracers that leave a record of history and of prehistory. This is the journey on which we will soon embark. But first, we must connect this mathematical model of the microworld to the world we experience through our senses. How atoms let you touch, hear, see, taste, and smell will be the subject of our next lecture.